The title of this presentation is, of course, Best Practices for Effective Process Filtration Planning. My goal with this webinar is to take you through my many years of experience in the industry in about 30 minutes or slightly more, sharing some of the most important tips for proper system design and component selection as it pertains to the filtration equipment used in food and beverage. So I've seen them all, from the non-existent to the overbuilt and unnecessarily complex arrangements, and I'm hoping that some of these points made today can be applied to create a better future with even safer products and more profitable production for all of you. So the presentation format is going to be quite simple. I'm going to first start out with the benefits of filtration and what process filtration really is, focusing on why it's a critical consideration in the design of modern food plants, and also to highlight some of the benefits. So I'll discuss some of the basic filtration principles, guide you through some confusion and difficulties present in an industry that deals with things like microorganisms and submicronic contaminants that you can't see, and I'll help to proactively plan and ensure relevant regulations are being met, food safety audits will be passed with ease, and best practices are understood. And lastly, the majority of the time will be spent focusing on the best practices of the system design itself, learning about things like the best ways to set things up, and arguably more importantly, understanding how not to do things. But before we start, I'll give a brief introduction to myself and my background. So, of course, my name is Coulter Marks. I'm the engineering manager, as mentioned earlier, in Donaldson's process filtration business. We're a division of purely filtration-focused company that specializes in food and beverage process applications. I've been with the company for a total of 7 years, starting out as part of a group focusing on diesel fuel, water, and dirt separation for engine applications. And after doing this for nearly 2 years, I transitioned to an engineering role in the food and beverage group, and ultimately today to engineering manager. We're a global organization set apart in the market by our advanced technologies, high product availability, and unrivaled support and expertise, and our mission is to be the first choice in product and process integrity. So the first question that needs to be answered, of course, is what's the point of this? It's really easy for all of us to get buried in the never-ending list of daily tasks, but it can often be more difficult to take a step back and focus on some of the problem prevention controls, such as filtration, that can have a dramatic effect on the overall profitability of a plant in the intensely competitive food and beverage market. And by problem prevention, I mean a whole array of different things that might impact an operation on any particular day, but all produce more or less the same negative consequences, especially avoiding things like line down situations caused by upset conditions, avoiding maintenance costs associated with poor component protection and equipment wearing out prematurely, spoiled or scrapped products that didn't meet QC or shelf life expectations, and things like being green, taking advantage of newer technologies that were developed to operate efficiently, minimize overhead, and preserve the planet, ultimately protecting both consumers' health and preserving their image of the producer as a trusted, high-quality manufacturer. So to be a high-quality manufacturer, one needs to have a good quality control, and this looks like many different things depending on the product, its unique risks, as well as the intended consumer and their risks. For example, in the food and beverage industry, and specifically dairy, we have a product that is particularly susceptible to contamination by spoilage organisms and possibly pathogenic microbes. So there's a focus to ensure that the maximum amount of shelf life is reached, creating a repeatable, stable product. And part of this equation is ensuring that there is as near to zero as possible spoilage organisms present in the product. So microorganisms typically grow, of course, in an exponential format, and they're usually of minimal concern so long as a small enough concentration exists to not really matter. But when conditions are right, they can grow like crazy. So it's important to begin with as few as possible. For example, starting with 2 colony forming units instead of 16, they're both really low numbers, but that might be the difference between days of reproductive cycles that could lead ultimately to a dangerous concentration. So types of contaminants in these systems. I think before getting into the details, it's helpful to first get an idea of the contaminants in the system that we're targeting. Most of these things are invisible to the naked eye and represent the comparative sizes will help wrap our heads around and relate to some of these things that we'll be discussing in more detail in the coming slides. So as you can see, I put a black box around bacteria as it's really the true focus of this message. Bacteria are on average from under 1 micron up to about 10 microns. In between the sizes of things like cigarette particles that are a little bit smaller and the droplets that form clouds that are a bit bigger. Another thing that will help give reference here is that a human hair on average is around 100 microns, and the limit of vision for the unaided eye, of course, for people that have really good vision is around 40 microns. So these are really quite small things that we need to deal with in these systems. When it comes to filter selection, it's really important to use true sterilizing grade filters at points of use in critical applications. So why is a sterilizing grade filter rated at the 2 micrometer size, and why do we feel this is really important? Well, it basically has to do with the fact that 0.2 micron particles can be some of the most difficult to capture. The chart on the right of this slide shows that the minimum retention efficiency of a gas filter occurs somewhere in the 0.2 to 0.3 micron range. And it's called in the industry the most penetrating particle size, or MPPS. And the test organism used to rate the filters has this size as well. That's why they're rated at 0.2 micron. So don't go out and assume that if you find, for example, a 0.1 or 0.01 micron rated filter, that it's actually going to be effective at this 0.2 micron size. The industry in general has kind of polluted the topic and made it difficult to understand, since it's typically counterintuitive that very small particles can actually be easier to capture than some larger ones, but it's true. So on the left, you can see there's several different mechanisms that work to capture different sized particles from a fluid stream. And the largest and most obvious is sieving. Everyone's familiar with this concept. That's where the particles are physically too large to pass through the pores of the filter media, and it really only works on big stuff like sand and moths and cigarette butts and other really big contaminants. But remember that a filter's job is to produce a clean fluid stream, so it must still allow the molecules of the fluid and the fluid itself to pass through, and therefore needs to have some sort of pores or openings in the media. But it also must catch very small things like bacteria. So it can't always do this simply by sieving, or it would just clog up very quickly and become unusable. So instead of some of these other mechanisms come into play. For medium-sized particles, for example, we rely on the fact that they have some inertia still and will not be able to follow the fluid stream as it changes directions, navigating that complex filter media fiber arrangement. And at the other end is diffusion, or random movements of very small particles that are imparted by other molecules in the fluid stream and the energy of the system. And that random or Brownian motion will increase the likelihood that the particle will contact the filter media. And that's really where the magic happens. Once that contact has been made, things like electrostatic forces will cause that particle to remain adhered indefinitely. So now that you know a bit about the contaminants that are captured, let's look at some of the filter medias that are used. So the most common formulations of medias used in food and beverage applications, they all have pros and cons, and the options exist so that the best choice can be made after understanding design intent and application details. On the left, we have a membrane filter. It looks a bit like Swiss cheese from the top, but that actual internal structure is quite complex. You can actually see the pores, and you can imagine a bacteria, for example, being captured because it can't fit through that pore, similar to how a chain link fence would stop a baseball. In the middle picture, we've got a sintered material. So this makes it for a very tough and robust chemical and heat resistive media for things like culinary steam production. Most of the other media materials would melt in that environment, so we need to have stainless steel. And on the right, we have a depth filter. Depth filters are just random arrangements of fibers, and they typically have advantages of being able to flow or process higher volumes with less restriction in the system than other media like membranes. So the depth media captures particles in the same way that a tree catches a golf ball. So if you can imagine, or I'm sure many of you on the phone have been golfing, there's a lot of spaces between the tree branches that are much bigger than a golf ball, but at least in my experience, every time that you try to punch one through a tree and get back on the fairway, the tree catches the ball. So they're pretty effective at removing things, even though there's certainly possibilities where the spaces between fibers are larger than the contaminant itself. So let's point out that there are some differences, first of all, between terms. Regulations are things that must be followed and adhered to. Best practices are important, but not necessarily tied to a legal authority or regulating body. They're more voluntary than regulations. And in the U.S., the most popular regulations are produced by government bodies like FDA, Department of Health, USDA, etc. These bodies are responsible for many things, including inspection, as well as defining safe ingredients and process equipment materials. The best practices are usually voluntary. However, one could argue they are, in effect, also mandatory because they could be requirements of some of the largest customers and retailers of food producers. So popular examples in the U.S. include things like 3A, which has historically been quite dairy-focused, although in more recent years is certainly expanding into any type of food production. SQF is extremely popular across the country, and most of the plants that I visit, you certainly see an SQF plaque somewhere in the entryway. And I've also added things like BRC, for example, to point out that there are actually quite numerous different schemes that are accepted around the world, and different ones are more popular depending on the particular geographical region of the world. So even though they aren't law, many times those things that end up being the basis for a regulation in the future are the best practices. So they arise through innovation and creativity, both by suppliers and producers, often by voluntary contribution of the people that have also full-time day jobs, but also participate in working groups and meetings of the standard organizations to really bring together some of the best minds in the industry and share ideas and experiences for others, often their very own competitors, to benefit directly from, all in the name of safety and progress in the industries that are served. So the Global Food Safety Initiative, GFSI, is a business-driven initiative for the continuous improvement of food safety management systems, ensuring confidence in delivery of safe food to consumers worldwide. GFSI provides a platform for collaboration between some of the world's leading safety experts, from retailers, manufacturers, and food service companies, service providers associated with the food supply chain, and international organizations in academia and government. It was launched around 2000 following a number of food safety problems where consumer confidence was at an all-time low, and since then, experts from all over the world have been collaborating in numerous technical working groups to tackle current food safety issues defined by GFSI stakeholders. So key activities within this organization are the definition of food safety requirements for safety schemes through a benchmarking process. It's thought to lead really to recognition of existing food safety schemes and enhance confidence, acceptance, and implementation of third-party certification, along with the entire food supply chain. So the focus is on extending the requirements to cover all the scopes from the supply chain, as they would call it, from farm to fork. Other important current activities include the development of a capacity to build a program for small and less developed businesses and to facilitate their access to local markets, and continuous focus on food safety auditor competence to bring industry experts in collaboration with key stakeholders. Now, an SQF program is one that's really relevant in the U.S. I mentioned that I've seen this everywhere. I know that they're highly established, especially in the United States, and really they're recognized by GFSI, as are several other ones that are not going to be mentioned in the presentation. The SQF family of food safety and quality codes are designed to meet industry, consumer, customer, and regulatory requirements for all sectors of the food supply chain. The SQF standard is broken up into modules depending on the type of facility and application and work involved. And within these modules are the actual guidelines specific to that particular application. So in many cases, similar concepts like, for example, the requirement of water quality can be the same for multiple modules. So the SQF code meets the needs of all the suppliers in the food industry through an internationally recognized certification system featuring an emphasis on the systematic application of HACCP for control of food quality hazards as well as food safety. So the implementation of an SQF management system addresses a buyer's food safety and quality requirements and provides the solution for businesses supplying local and global food markets. This, of course, fits naturally very well into the topic of the presentation, which is filtration. Filters are risk minimizers. So along with proper identification of the critical control points and the hazards associated, whether it be a utility like steam or compressed air or food ingredients and finished product, there is a filter available that was designed to fit into these processes. So let's quickly move around the wheel and mention each specific point. The titles of these wheels are the general formats of this critical control point plan. And starting at the very top with hazard analysis, the point here is that things like unfiltered compressed air, steam, or liquid might have contamination and are therefore identified as hazardous. So once we identify a hazard, we have to understand where these things could cause problems. So anywhere that compressed air, steam, or liquid contacts or becomes part of a food product is a critical point needing control of that hazard that was identified. Number 3 is critical limits. So defining what degree of filtration, and this would be measured by terms like efficiency or LRV, logarithmic reduction value, is required to eliminate the hazard at each critical control point. Monitoring. So this would be, as it relates to filters, things like integrity testing, monitoring of the delta P or pressure drop across the filter. And another way to say that is what state of operation it's in. Is it new or is it used? Is it nearing the end of its life? Sterilization cycle count or replacement intervals on a preventative maintenance basis. Number 5 is corrective actions. Determining the cause and system correction when a deviation from a critical limit is identified. So this might be an example of, I've identified that the integrity test was not passed and what needs to be done to get rid of that problem in the future. Number 6 is verifying the procedure. So determining the cause and correction when that deviation is identified. So one example of fixing a problem that was mentioned of it didn't pass integrity would be, well, let's maybe replace it more frequently. It seems like it's getting to the end of its life sooner than we thought. Replace it more frequently, possibly change the conditions in which it's being sterilized to lower the temperature and pressure of the system. There could be several different solutions, but really this is to verify that the correct problem has been identified, the root cause of the problem, and verify that it's being corrected. And lastly is record keeping. So out of all these things, they're all very important, but they're not worth a whole lot when we don't have records of what was done. So this is really a summary including the rationale for steps defined in a plan, including, in the case of filters, again, things like the status, the monitoring records, the replacement records, the sterilizations, when they happened, what time they happened, what temperature they were performed at, things like that. They're the things that are important to show that we're actually doing what we're saying and we're saying what we're doing. So to summarize, the first step is identifying the risks, and these risks can come from one of several different places, but what's really important is to consider and address the unexpected. So think about, for example, an air compressor. Let's say the air is used to blow open a package before filling with a food product. That intake air for the compressor is on the outside of the building, normally intaking pretty clean outside fresh air. And that's fine, but what happens when the city decides to do some work on the street next to the building? And now you're producing not only compressed air, but also compressed diesel exhaust and cement dust and asphalt smells and things like that, and applying that mixture directly to the food product or packaging surface. So things like this are relatively unlikely and infrequent, but it's a real threat, and it's happened many times in the past. And again, the point is that preventing this from happening is better than reacting to it after it's happened. So I'd like to spend the majority of the presentation in the second half here talking about these three utilities and exactly what the best practices are within each of them. So they all have unique aspects to them. They all require different attention to different details. And I'm really trying here to share with you what are those things that I've found time and time again that were either just didn't make any sense, were wrong, or were discovered to be a better way of doing things. It might not be popular or common knowledge yet. So we'll start with culinary steam. Culinary steam is really any steam that's used in direct contact with a food product. So it usually becomes part of that product itself as an ingredient as it condenses and gives up its heat. The common applications are pretty broad, depending on the product being produced. For example, in bakeries, it's often used during the proofing process and regulates both the temperature and humidity in order to ensure the product's risen to the full size without becoming too dry due to the tendency of heat to evaporate. It's also the preferred method for cooking most of the pre-cooked products. It's really for good reason too. It steams constant temperature. It naturally finds anything that's not up to the temperature and condenses and warms it up. It's great for highly controllable mass production cooking or intermediate production steps like blanching. After a CIP and before the next production run, culinary steam can be used to sterilize and help to clean that equipment in the production line. And in any of these cases, the steam sees the product either directly or indirectly and therefore presents an identified risk that must be controlled using a culinary steam filter. So the contaminants in these systems, they're quite dirty, steam systems in general. The high temperatures in these systems accelerate corrosion and material degradation, and the aqueous environment presents special challenges for pH control. Less than ideal feed water makeup precipitates minerals once it gets warmed up that end up being hard particulate contaminant in the system. And these can all present risk ranging from less dangerous situations like equipment clogging or failure to more important risks like food contamination from metal or other system materials. So either way, the problem is costly and critical to control. So culinary steam best practices. The most important design consideration I've found in these systems is really to ensure proper liquid drainage. So steam is constantly condensing into water as it gives up its heat energy, and as it does this, that very water that produced the steam can turn into its own worst enemy. So the problem with water is that it can create high velocity slugs of liquid within the system that can create very damaging impacts to components like valves or filters, and proper drainage is critical. So every low point in that system needs to have a drain valve. It also helps to pay close attention during system startup to ensure that the entire system is brought up to heat in stages. So slowly bring up the temperature is going to avoid the entire system from becoming overwhelmed with water and ultimately causing problems. So next, follow already established guidelines like the culinary steam best practices published by 3A. It contains all the useful information that's needed to produce a proper system and will avoid any important steps being missed. It's something that's easily available online. It's a reasonably low cost. There's really no reason to not use something that's already been developed to try to cover all of these bases. And thirdly is use filters at points of use. So I've seen tons of systems where this is a single large filter located centrally, usually near the boiler, and then supplies a header and several points of use throughout the plant. And this is helpful. It's better than nothing, of course, but it really doesn't address all of that contamination which is generated in the pipes between the filter and the point of use. So the recommendation here is place the filter at or as close to as possible the point of use, and then use only stainless steel after the outlet of the filter to minimize the chance of any corrosion or new contaminants being introduced to the fluid stream. And lastly, pay attention to the technologies on the market, especially when working with a low pressure application. So we usually consider those the things that are under around 15 psig. So there's not a lot of pressure in these systems to work with, and well, maybe a 3 psi pressure drop through a filter might be okay on a 100 psi system, representing about 3% of available pressure. That same 3 psi on a 15 psi system is now about 20% of the available pressure. So it's important in these applications to use something like a pleated filter with much more immediate surface area available compared to the typical cylindrical stainless steel sintered powder media that was mentioned earlier. So compressed air is the next utility I'll address. As you can see from the system diagram that's on this slide, there's several more components in this system than there are in the culinary steam system. And that's really because the array of contaminants in a compressed air system are quite a lot more diverse than in the steam system. So sterile air applications include things oftentimes similar to culinary steam. They're those applications where the compressed air contacts or becomes part of that product directly. So the applications include low pressure blanketing of products in ingredient tanks to ensure, for example, that no outside contaminants can enter that tank space. Drying of the systems with sterile filtered air after steam sterilization. So maybe you've sterilized the system with the culinary steam that was just mentioned, and now before you can produce again, it needs to be dried out. That would be sterile air to dry that system out. They can become part of things like whipped products or certain types of fillings, blowing open packages before filling with food, using the compressed air to push, for example, a pig through a line to recover product and clean the line, and applications like blowing the small PET preforms into a full bottle, for example, for soda or bottled water shapes. The contaminants in these systems range from anything that can enter the compressor intake from the ambient air to the contaminants that are generated in the compressed air system itself from mechanical components. So air compressors are mechanical and therefore often lubricated with oil. This oil can be sent downstream. The humidity in the atmosphere will condense into liquid water as the compressed air cools, creating another contaminant. When this water and the compressor oil mix, they can form a pretty nasty emulsion that's really a great breeding ground for microorganisms. So they'll sit there at that interface between the water and oil, and they will drink the water and eat the oil, basically. It's a great growth environment for them. So as a reminder, these contaminants are all dangerous to food quality and consumer safety and really need to be treated as hazards when that air contacts the food or the food packaging surfaces. So the best practices in these systems, one of the most important yet overlooked sterile air best practices is keeping that air as dry as possible. This is important because just like people and animals, microorganisms need water to live as well. So we can catch them with filters all day long, but in combination with that technology, it's a best practice to take away one of those variables the organism needs to survive. So these variables are water, food, and a home. The first three things that you'd look for if you just woke up stranded in the rainforest. The heat of the air compressor and the pipe fittings in the system provide really great warm and cozy homes for bugs, and it's really easy to remove the water from the system and take away that opportunity to proliferate. So the best technology for doing this is a point of use desiccant dryer. Keep the air dry. That's going to make the system as least susceptible to contamination with microbial contamination as possible. Another best practice to focus on is proper pre-filtration. And by this, I mean those items that are dealing with the bulk of the water and the oil and the dirt so that sterile filter at the point of use can do its true job effectively, which is retaining bacteria. If that sterile air filter is being hit with every contaminant in the system, it'll become overwhelmed and defeated, and it really needs to be protected with the proper things upstream. So similar to steam systems, liquid's a big issue in compressed air systems. It needs to be drained away. A typical plant might have several dozen of these drain points. A good tip is to use what are called zero-loss condensate drains. So these are special drains in the system that allow the compressed air condensate to escape while the condensate's drained away. So it basically cuts off any of that compressed air from being a loss, and it can drain away the liquid effectively without wasting compressed air. And it really can result in quite considerable energy savings due to conserving that compressed air in the system. Require bacterial retentive designs when they're needed. So this is important because the filtration market is full of the misleading claims that I mentioned earlier. Don't assume that the 0.01 micron sticker on the filter means it can effectively retain bacteria that are larger. So I pointed this out earlier in the presentation. Just make sure that you understand that there are some things that can do it and some that can't, and make sure that the ones that are capable of doing the job have the associated documentation with them to state that, so you can have that on record. And lastly, steam sterilized air filters. So as they operate every day, they're sitting there collecting millions of bacteria, which can in and of itself form a hazard. If you're essentially making this concentration of bacteria, and if something happened that you didn't expect, a process upset, that filter could be compromised and ultimately send a higher than normal concentration downstream. So hitting that filter with high temperatures from steam will kill off any of the viable organisms and ensure that they're not capable of reproduction. So along with steam sterilization comes the proper maintenance planning and replacement of consumable parts like the elements inside. They can't operate effectively forever. So the last system is the liquid system. Usually this means water. Water is the universal solvent and a requirement of life, and it's full of potentially dangerous contaminants, of course, because of that. So liquid applications, again, this is not anything unexpected. It's used for a wide variety of applications. The most important is when that liquid or water itself is an ingredient or the final product itself. And depending on the product and the additional ingredients that are added and whether or not that product can handle a thermal treatment, it'll really determine what is that risk and what filtration controls need to be established to remove that risk. So I've listed a few different types of liquid products here, and you can see that different products will have different risks and contaminants. So as you can imagine, things like a juice might be more prone to contaminant like insects, insect eggs and yeast that could turn that fruit into a wine. Wine quality could be affected, for example, by recarbonation in the bottle if all of that yeast isn't removed. So that's especially when you're balancing the sweetness, adding sugars back into the wines that are produced in regions, at least that I'm familiar with. I live in the Midwest, and I know that they do a lot of that here because the grapes grown in this region aren't quite the same sweetness as the ones that are grown, for example, in warmer climates like California. So you've always got to add back a little sugar to balance, but you can't risk giving that yeast more food to metabolize into more alcohol and carbonation. Otherwise, you'd open a bottle of what you expect to be a smooth wine, and it will end up being something like champagne. So they're both great drinks, but you want to make sure that you're getting what you're thinking you're producing. Beer can be affected by contaminants like diatomaceous earth that are used in the production process to filter out yeast. So the thing that's doing the filtering can actually become the thing that needs to be filtered out, which is a bit interesting, but it's true nonetheless. So it's really important to focus on what the actual product is and what the contaminants or risks to that particular product are, because they could change depending on what we're focusing on. So best practices in liquids require really focus on pre-filters. Liquids are a lot more viscous than gases, and therefore they hang on to contamination much more than gases. So they're often, in effect, dirtier. So it's important to design systems with proper pre-filtration so that the more expensive final filters that are doing that sterilizing job can remain in operation for as long as possible. You don't want to be clogging up these final filters unnecessarily quickly when you could be clogging up something that's cheap and protecting that like a pre-filter. Pay attention to the construction of the elements, the filter elements inside the assembly. Again, similar to the steam elements, a pleated element where the filtration media is folded back and forth like an accordion shape, they really offer many advantages over some of the older technologies like melt-blown cartridges that have only a fraction of that exposed surface area to do the work. Similar to compressed air applications, the systems and the filter elements need to be sterilized or sanitized with hot water on a regular basis. This will, of course, avoid microorganisms from forming the very difficult to remove established colonies that can form if they're left long enough in a hospitable environment to be able to thrive. And lastly, pay attention to the sealing design used in these elements. So there are not a whole lot of different options available. They're pretty well established in the market. You're not going to find a huge array of different designs, but the two most popular are DOE, which stands for double open end, and that's a design that is really axially compressed between a couple of what are called knife edge seals, or just sharp edges in the housing that press into that cut off open end of the filter. And there's another design that's popular that uses two O-rings. And whenever it's an application that really matters and the filtration of critical importance, you really need to use the double O-ring design. A lot of the same medias and same models can be had in either connection, and the double open end tends to be quite popular because they're oftentimes low cost comparatively with the double O-ring designs. But the double O-rings are just much, much better and more effective at producing a true seal in an application that really matters. So the first O-ring on those elements is really used to clean that sealing area so that when the second O-ring makes contact with the housing, it's really going to have a perfect and uncompromised seal. So I would say that's one of the most important ones. You can design a system and have the best intents with it, and only to find out later on that something you weren't unaware of, like the element connection type, was not effective for the purpose. There's good ones and there's not as good ones, and just understanding that there's a difference and there's a more appropriate one for that final filtration spot can have a big effect on the overall effectiveness of the system. So I've shared some technical details about filtration, identified some of the risks and proposed solutions and best practices. Filtration is, of course, a very effective and low-cost way to deal with some potentially very large and damaging problems, ultimately providing an insurance policy to both producers and consumers. So I hope you've all been able to take something away from this that will make your job easier, your customers safer. And with that, I'd like to say thanks for your time, and I'd be happy to either address any questions that you might have, or certainly follow up with you in person if it's more appropriate. You can feel free to reach out to me anytime. I'm here every single day. And I'd be more than happy to help you out with whatever might be of concern to you. So with that, I'll say thanks again. Hope everyone has a great day, and hope to hear from you sometime in the future.
Thank you, Coulter. At this time, any attendee with a question, use the dashboard to raise your hand or type it in. We'll allow about 30 seconds to a minute to see if anybody has a question for Coulter, and then we'll end the broadcast. I see a question here. Will the slides be sent to participants? You can find it under the handout section, and we'll also have it on our website in the members only section for FTSA members. But if you're on this right now, you can get it from the handout section. Question here from Holly. There are quite a few control and filtration points. Do most plants have a dedicated person to filtration?
So that's a really good question. I'll give a couple of different answers. There usually is somebody that's dedicated to it, and by dedicated I mean responsible for. So this could be somebody in the quality control area of a plant, because as mentioned several times, the filtration really is technically part of that quality control portion, but there's also a maintenance aspect to it. So some plants may have the maintenance manager or any of the maintenance staff also responsible for the maintenance of the system, which includes the replacement of the filter elements. So between quality groups and maintenance groups, one of those two is going to be likely the most appropriate contact for the operation of those systems. And when it comes to the design of the systems itself, it's usually somebody like a plant engineer who's part of that process, or a process engineer is often the title, and they would be responsible for the specifying of and choosing what equipment goes in for that purpose.
Great, thank you, Holly, for the question. Any others? From Jerry here. Could you shed some light on starch filtration of cooking water?
Starch is some nasty stuff, and it's hard to filter. It can be very difficult. There's a lot of different technologies available. I would say that it really depends on the application and what kind of loads are being dealt with, but generally, a filter sometimes might not be the best way to deal with something like that. It really does depend on details, and I don't want to be too ambiguous with the answer and skate around the question, but starches are very difficult. They're sticky, they're nasty things, and they may be best removed by other technologies sometimes. We've done some different testing with a lot of different starch applications, and again, depending on concentration, it may or may not be the best thing to use.
All right, thank you for that question, Jerry. Any other questions? All right, well, thank you, Coulter, for your time. Thank you, everybody who's joined us. Oh, one more question here. Is it common to expect some sort of certification from filter suppliers backed by published testing?
Yes, it certainly is. I would recommend that whatever you're choosing, you ensure that the manufacturer, whoever you're getting it from, is able to supply you with, when it comes to bacterial retentive filters, of course, something that shows that filter has been tested truly in a bacteria environment. So there's an ASTM test that is available that shows that the filter really, it must pass a test. It's a pretty rigorous test. It has to be able to retain at least 10 million bacterial cells before one of them can get downstream. And that's per square centimeter of filter media surface area. And there can be hundreds of square centimeters. So that would be the test that qualifies a filter as a bacterial retentive filter or a sterilizing filter. And then second to that, since testing of that filter is very important to ensure that it's doing its job effectively over its entire lifetime, you really need to also make sure that there are in place integrity tests that are non-destructible that can be performed, and those tests need to have the results correlated to that original true bacterial retention test. So those two things are extremely important. When it comes to things like compressed air filters upstream of that, I would recommend ensuring that documentation is available that shows the filter has been tested by a third party rather than the manufacturer itself. It's of course, manufacturers are testing them to make sure that they're producing a product that is likely to meet the third party test, but ultimately you want to make sure that you're not taking the person selling the product's word for it. They should be able to be invested in it and supply a third party validation of the test data that corroborates the claims they're making in the data sheets.
Wonderful. Thanks for the question, Norman, and thank you, Coulter. All right. Well, appreciate everybody joining us here this afternoon. Again, you can find the handouts here in the side pane, and if you have additional questions, you can contact us. And again, thank you so much for your time. Hope you all have a fabulous rest of your day.
Thank you.